Okay, so in the impulse chapter, we're going to be dealing with Newton's law, F is equal to ma, but we're going to rewrite this law in terms of momentum. So we're going to say F equals ma, and then A we're going to express as dv dt, and then we're going to take the m and put it into the dv dt. We're going to write it this way. And then we're going to have F is equal to dp dt. So we're going to define a constant, a function called momentum, and its definition is mv. And that's the definition. The units of it would be kilogram meter per second or slugs feet per second. Then we're going to say force is equal to dp dt. So this way of looking at it, you say when a force is exerted on a system, it causes the momentum of the system to change, right? F equals dp dt. And the rate of change of the momentum is equal to the force, right? Then we could say F dt is equal to dp, and then integrate that, and then define this as impulse. Impulse is the area of the force times time, the force over time. So it's Newton seconds, or pound seconds. So the impulse would be how much impulse you are imparting on the system is how much force you're exerting spread out over the time that you're exerting that force, you see? And then the impulse on the system will cause its momentum to change. So then you have impulse is equal to change in momentum. So it's kind of like we just redid and redefined Newton's law, F equals ma, in terms of impulse and momentum, okay?
When you integrate the dp on the other side, the d stays positive.
Yeah, integral dp becomes delta p. P final minus p initial.
Oh, that's a delta.
That's a delta. So where does impulse come in to play with certain applications of impulse? Well, one application of impulse is to, like in collision type problems, suppose somebody is jumping from a burning building, right? Which reminds me today, the cathedral in France is burning. Wow, it's crazy. The Great Fire of 2019, they're gonna call it. So if somebody's jumping from a burning building, and what is the reason that we put a mat here, like a sponge type mat? So upon striking the mat, what's gonna happen? They have an initial momentum that is going, P initial, just before hitting, which is going to equal to their final momentum that they had as they were, you see. So when you're going down, you're gaining velocity. So just before you're going to hit the mat, you already have an initial momentum. Then eventually, you're going to come to rest, and your P final is going to be 0, right? You're going to come to rest. So the impulse is going to equal integral of force dt, right? And then that's going to be momentum final minus momentum initial. Momentum final is going to be 0, right? Momentum initial is going to be mv initial, right? And then what is your v initial going to be? It's going to be, since you're going down, we can say your v initial is actually negative, right? So momentum final is 0 minus momentum initial. V initial is going to be negative, and what is that V initial going to be? If we can ignore the effect of air friction, it's just simply going to be twice the, what? Your potential energy is equal to your height. So if we measure the height from the top of the sponge, h initial, right? M cancel. So V is equal to 2gh initial square root. So that is your final velocity that you have when you go. And that becomes your initial velocity upon impact with the sponge, right? So then V initial is going to be negative square root of 2gh initial, right? So then that's going to be the impulse that is exerted on you, right? So whether or not, let's say you have two people jumping from the same height. This guy jumps, there's no sponge. And this guy jumps, there's a big thick sponge. What's the difference? Is the impulse imparted on both of them the same? Or are they different? This guy jumps, his final velocity is still the same, right? And he also eventually stops, right? But most likely he's splattered all over the ground, right? So what is their difference? He still has the same impulse.
He's not the one faster.
The difference is the intricacy of what is happening to the force over the time, you see? So what this one is saying is the impulse, the same impulse can be imparted over a long time period versus a short time period, right? If you have a long time period that you are in contact with that system, what it does, it kind of flattens out the force. So if we were to plot the force here as a function of time, as soon as you hit the sponge, the force that the sponge exerts on you starts to increase, right? Then somewhere in the middle, it probably reaches its max, and then the force begins to decrease. Or maybe does it continue to increase? Probably continues to increase, huh? Because it's like almost like a spring. The more you compress it, the more force decreases. Maybe it continues to increase, huh? Until you finally come to rest. Then it stops. So the area under this, right, the impulse, the meaning of the impulse is the area of the force times t, right? But here when you hit the ground, it's more like a spike, right? This area and that area are equal. It's the same impulse, right?
It's gonna go very high.
But here, the force that's needed is much bigger because it has to have the same area, right? So, for example, let's say your mass was 100 kilograms and your height was 50 meters. So what would that equal? What would the impulse be? $3,130. Newton seconds. So the In other words, in order for you to stop, something has to exert an impulse of 3,130 Newton seconds on you, right? Well, if you then increase the time of contact, let's say this is one, what would be realistic? Let's say something like 2 seconds for you to come to rest. That might be too slow. 2 seconds? Maybe 1 second, yeah? Okay, 1 second. So then, force times 1 second. So that means the force has to equal what? The force has to equal 3,130 newtons. Okay. Can your body withstand that much force? I'm not sure. I mean, our bodies weigh, in newtons, our bodies weigh about 900 newtons. 8 to 900 newtons. That's 3 times our weight. Maybe we can, maybe you'll still have a broken something, but it's not going to be as bad, right? But over here, you stop in 0.1 seconds or 0.01 seconds, right? So depends if it's grass or concrete, right? Grass, you might take a little longer to stop. Concrete, you stop right away. So if it's 0.1 seconds, so then you're going to have here 0.1 instead of 1. So the force is going to be 31,300 newtons or 0.1 seconds. Now we're talking a lot of force, you see. So hence that's why we use airbags also in cars, right? To stop people when a collision happens. Because either way, your body has to stop. When somebody hits you from the back and you're going to come to a stop, you're going to experience the same impulse. One way or another, you're going to experience the same impulse. So what do? We increase the length of time that it takes for you to stop. If you don't have the airbag, your body will just keep going and then the wheel will stop you right away. Boom, right? Very short time, crack your ribs, you see? But if you have the airbag, now the airbag pumps up and then you see the time. By the time your body goes and hits the wheel, it's more or less already stopped. So we're increasing then the length of time. You see, it's a very good idea that impulse is used. Also, the concept of impulse is used in collisions. When two objects collide and there's a collision, we can argue that the impulse on the system, on the net system, is 0, right? So when a block is coming like this and another block is coming like this, and let's say there's no other forces on the system, no friction and no other forces. The only forces are the mutual forces that they exert on each other, right? So this block hits this guy hits this guy, but let's say no other thing acts on the system. Therefore we can say when two objects collide with each other and there's no other forces on the system, the net impulse on the system is 0, right? So J total on system is 0. Well, in that case, if the net impulse is 0, that means the net change in momentum of the system is 0. So from there we get the idea of momentum conservation, right? So delta P of system is 0. So from there we get the next set of types of problems that we're going to do, known as momentum conservation problems. So let's do one-dimensional motion, and we can do two-dimensional. One-dimensional collisions. So we can divide it up into perfectly inelastic, perfectly elastic, and then semi-elastic. Okay. In all three of these cases, if there's no net force on the system, then we're going to assume that the impulse, the momentum of the system is conserved, right? So perfectly inelastic, what's going to happen? An object such as a 2 kilogram object, let's say, so in a perfectly inelastic, they're going to come and stick to each other. The two objects stick. And then they move together with a certain velocity. So the question can ask, what is the final velocity of the system? And what is the percent loss of kinetic energy? Right? What is B final? And then B, what is percent loss of energy? So how do we do that? Well, the momentum of the system is conserved, right? So we're going to say the initial momentum total must equal to final momentum total. So initial momentum is what? 2 times 3, right? But remember, momentum is a vector. So it's not like kinetic energy. With kinetic energy, if you're going to the left or to the right, you still have the same energy because it's half mv squared, right? With momentum, the direction matters. It's a vector. So if your momentum here is 3, this guy's momentum is negative. So they're opposing each other. So you have here 2 times 3 plus 5 times negative 1. Right, is the momentum of that guy. Now, when they stick together, they act like one object whose mass is 7 kilograms. Now we can find V final. 6 minus 5, 1. The final is very small because their momentums kind of cancel each other, right? And then they come and hit each other. Who wins? The 2 kilograms still wins because it's moving faster, right? The 2 kilogram is like a 200-pound running back going at 30 meters per second. This is a 500-pound lineman running at 10 meters per second. Who wins? The 200-pound running back. But who's gonna feel it afterwards? I would hate to be the running back. Even though I won, I'm gonna go to my locker and I'm gonna go, oh, what the hell? Oof. You know, I won, but it cost me my back. So the V final is 1/7. Okay. So what is the percent loss of kinetic energy? So the initial kinetic energy of the system see, with kinetic energy, you don't care if it's going to the left. It still has the same energy, you see? So then you have your initial kinetic energy, 9 plus 2.5, 11.5 joules. What's the final kinetic energy of the system? 1.5 times what? Their total mass, which is 7, times their final velocity, which is 1/7 squared. So 1/2 the combined mass of the system plus 1/7 squared, and then you're gonna get what? 1/2 times 1/7, right? 1/14. Very small energy, huh? So basically half of this guy. like 0.07 something something joules. So almost all of the energy is lost. Where does that energy go? When two objects collide and stick, where does that energy go?
Heat.
A lot of it goes into the energy of whatever is causing them to stick together. Why do two objects stick in the first place? Maybe one object gets embedded into the other one, right? Or it could be that maybe this is a magnet, South Pole, North Pole, South Pole, North Pole. Maybe they get stuck because they're magnets. So the energy goes into the energy of magnetism, you see? So whatever's causing them to stick, either it's the objects are kind of, maybe they're deformed and one car goes into another car. That could be, goes into the damage of the cars, So what's the percent loss of energy? Is kinetic energy initial minus kinetic energy final over kinetic energy initial. Kinetic energy initial was 11.5 minus kinetic energy final is going to be 1/14 over kinetic energy initial. 11.5 minus 1/14 over 11.5. Well, that's almost like 100% loss of energy. Times 100. 38. So that's the worst kind of collisions, is head-on collisions, right? More damage sustained. Because you're kind of coming and your momentums are canceling each other. So when you hit each other, it's not going to be fun. Your energy is lost, big time. Okay? Okay, with semi-elastic, how do I make it? The perfectly elastic is probably the hardest to solve because you have to conserve kinetic energy and momentum. With semi-elastic, it will might look something like this. In other words, with semi-elastic, the problem is going to give you more unknowns than the elastic case. With perfectly elastic, it's going to look something like this. So with perfectly elastic, it's going to say, solve what V1 needs to be, solve for what V2 needs to be in order to conserve momentum and kinetic energy, right? This guy is going to say, okay, I'm going to give you V1, what is V final? Okay, one of the unknowns is given to you. So then it's going to say, find V1 and percent loss of kinetic energy. We could do this one, and then Wednesday we'll start with this one. So with this one, what do? We do the momentum conservation again, right? Say, okay, momentum final is equal to momentum initial total. So what is momentum final? 5 times 0.2, but then this is going to the left, right? So its momentum is what? 2v final. And then the initial momentum was what? 2 times 3 minus 5 times 1, which was 1, right? Oh. So this is what? 1. Oh, B final is 0. So that's interesting. This guy comes, hits that guy, and stops. Is that a possible scenario? Yeah. It stops. This guy changes direction and goes backwards at 0.2 meters per second. So how much energy do I lose in this case? I should lose less energy than this one, the perfectly inelastic, right? So the initial energy of the system is what? Well, it's still 11.5, because I didn't change this scenario. It's still 11.5 joules. What's the final energy of the system? 1/2 times 5 times 0.2 squared. Because the other guy doesn't have kinetic energy. You see, I'm still losing energy, but not as energy as when they're embedded. You see? So that's gonna be what? 0.04 times over 2.02 times 5, 0.1. 0.1 joules, and then in the previous case, I had 0.07 joules. Yeah, so it is more. So the percent loss of energy, percent loss, 11.5 minus 0.1 over 11.5. So maybe 95% loss of energy or something, but not as much as the inelastic. Oh, it's still high. So you can tell there's a variety of cases that can happen based on the situation. They might hit each other, this might stop, this might return. As long as you're conserving momentum and you're losing some energy, semi-elastic, you can have many semi-elastic cases that are possible. But there's only one perfectly inelastic and perfectly elastic. So Wednesday, we'll solve this one, the perfectly elastic case. That one you conserve kinetic energy and momentum. Okay, good stuff. Now we're finally in chapter 9.